Hello everyone, welcome to the Makri Virtual. Hope you are doing good. Today I'm going to continue with your same topic, same chapter, that is memory hierarchy. This is the sixth chapter that we will study. In the last class we have studied about the cache memory, what is cache memory, what is the impact of cache memory, and what is the locality of reference. In the today's class I will discuss the memory hierarchy. So this is the topic that I will discuss in the today's class, that is our memory hierarchy. That is how different memories are organized one after the another. That is a memory hierarchy. So before that, let's take a quick review what we have covered in the last class. In the last class we have studied about the memory hierarchy continued. Characteristics of memory location with respect to the processor. The main target or the main topic of the last class is your locality. That is how cache memory will be organized in a different format, or how different location will be organized in the cache memory. So first topic we have discussed about the characteristics of the memory location with respect to the processor. Means what is a location, or what is where we store the data with respect to the processor, that is your CPU. So there are multiple concepts, or there are multiple points where we can store the data, like inside the CPU. That is inside the CPU means internal to the CPU, that is your main memory or temporary memory or in form of registers. Then inside the processors, inside the processor means inside the CPU, that can be performed or that can be done by using the L1 cache, that is using the cache memory. Then inside the motherboard, that is either in main memory or L2 cache. Then in main memory, that is either dynamic RAM, that is DRAM, and L3 cache. Then external means we can also store the data for the processor, for the CPU externally, that is outside the computer, in the form of peripherals. Peripheral means that is not internal, or that is not attached to the computer, but they are outside the computer, that are known as peripheral devices, such as disk, tape, and network memory devices. So these are the concepts we have studied in the last class with respect to the location of the memory, so that CPU or the processor can fetch the data and perform the operations that it will have to perform. Then we have studied about the memory capacity. That is, what is the memory capacity with respect to the word size. That is the natural data size for a processor. A 32-bit processor has a 32-bit word. That is, if a processor or the CPU has a capacity of 32-bit, so it can store 32-bit word. That is not that it will store only 32 bits. No, it will store 32-bit word, that is 2 power 32. So if a processor has a capacity of 16-bit, so it can store, or processor can store up to 2 power 16 word. That is, if a processor is of 64-bit, so it can store up to 2 power 64 processor or 64-bit word. Then we have studied about the various length that is used in the processor, that is your memory capacity. Then we have also studied about the addressable units. That is how we can address, that I told you, 2 raised power number of bits in the address bus, that I told you this is written. Then we have studied about the characteristics of memory, that is features of the memory with respect to the unit of transfer. Means how many bits he or she no, how many bits it will transfer. It means processor will transfer with respect to the memory. That is, the number of bits read out or written into the memory at a time is known as a unit of transfer. That is either internally or that is either externally. Then this is the access method, means how we can access the data or instructions from the memory. That is your next concept that we have studied. There are 4 types by which we can access the data. One is sequential, then direct, then random, then associative. Now we have discussed in detail one by one. That is, first is your sequential. For example, tape, that is magnetic tape. That is, every insertion or every deletion from the disk or from the tape can be done in a sequential way. For example, if I want to access the 5th record, then I have to go from the first to the fourth record to fetch or get the fifth record. Why? The main thing is that the data is stored in a sequence way. So if I want to get the, or if I want to fetch the fifth data or the fifth record, then I have to go to the go from the first to the fourth record. That is your sequential access method. The example is your magnetic tape. Then direct access method we have studied. That is how directly we can fetch the data. That is your direct access method. The best example is hard disk. We can directly access the data, directly jump to the location and fetch the data and then perform the operations. This is your random access method. That is, randomly we can pick the data from any location and then perform the operations. V means the processor pick the data or picks up the data, picked up the data and performs the operation. So till now we have studied three concepts: sequential, direct, random. Then next one is your associative. That is, if one thing is associative with another, that is one memory is associative with another memory, by which we can access the data, that is known as the associative access method. This said, addressing information must be stored with the data in a general data location. That is, the best example is your cache memory. As I told you, cache memory lies between the CPU and the main memory. So if the data is available in the cache memory itself, so there is no need to go to the main memory for the CPU. Simply CPU fetches the data from the cache memory, performs the operation and then displays the output. Then we have studied about the performance, that is what is the performance of access time, how we can access the data and how we can store the data. That is the time between requesting the data. Suppose I am the user, I am requesting for the data, and the time by which we can get the data or we can access the data, that is the access time. That is the time gap between the requesting and the getting it is known as the access time. And then we have studied about the RAM or the other types of memory, that is sequential, direct, associative. That is what is the access time in RAM, what is the access time in direct, sequential method. Then we have also studied about the memory cycle time, that is the cycle time that is used to fetch the data, that is equals to the access time plus the recovery time. Recovery time means if there is any problem, if there is any disturbances in the fetching the data, so that can be performed or that can be operated using the recovery time. So cycle time, that is one cycle is equals to the access time plus the recovery time. Then we have studied about the transfer rate, that is the rate by which data can be moved. It is known as the transfer rate. So RAM has a different transfer rate and the ROM has a different transfer rate. And the RAM transfer rate can be predictable, means we can predict the capacity of the RAM, that is equals to the 1 divided by cycle time. That is your RAM transfer rate. In the same way, if there is a known RAM, that is your ROM, that cannot be predictable, and that can be equals to the Tn, that is transfer rate, equals to Ta plus N divided by R. That is your known RAM transfer rate, that is non-predictable, that is not predicted in advance. Then we have studied about the physical types, that what are the types of memory that is used. One is your using the semiconductor, that the best example is your RAM. Then magnetic, that is your disk and the tape. Then optical technology, that is your CD and the DVDs, that is your compact disc and the digital versatile disk. And the other few concepts are also available for the memory, that is your bubble, hologram. Then we have studied about the physical characteristics, that is what is the characteristics with respect to the memory. That is your decay, that is less power, and the degradation over the time, that is your physical characteristics of the memory. Then volatility, that is RAM versus the flash memory. Erasable, that is RAM is versus the ROM, that is erasable memory. Power consumption means the part that is taken by the device that is more specific to the laptop, PDAs and the embedded system. These are the characteristics of the memory. Then organizations. We have studied about the organization, that is how we can organize the data. So organization means physical arrangement of bits into the words. That is how we can physically arrange the bits into the words, that is known as the arrangement of the or organization of the memory. Then not always obvious, non-sequential arrangement may be due to the speed of the reliability benefit. Then we have studied about the memory hierarchy. That is, what is memory hierarchy? That is the main topic of the today's class, that how we can perform the or how we can arrange the different memories in a hierarchy. This is the continued of the memory hierarchy we have studied. That is how when we go from the going down to the hierarchy, that is from top to the bottom, the following results will happen. That is decrease the cost, increase the capacity, increase the access time. That is the three main concepts that is used while going from the top to the bottom. This is the memory hierarchy that I will discuss in the today's class. Then we studied about the mechanics of the technology. That is, what is the technology that is used in the memory hierarchy? The same concept, increasing the capacity, decreasing the cost, increasing the access time. The main characteristics that is used in the memory hierarchy is your locality of reference. That is based on the principle that is known as the locality of reference. This is your exercise that you have to do in the lab or in the class. Then we have studied about the locality of reference. There are two types of locality that is used. And this is there are two types. One is temporal locality, one is spatial locality. We have studied about the temporal as well as the spatial locality. Then we have studied then when an item is accessed from the memory, it is brought into the cache. That is, if I want to access again and again the same topic or the same item, then we have used the or we have to use the temporal locality. Next is the spatial locality. When we access a memory word, we also fetch the next few words into the cache. That is known as the spatial locality. We have studied about this. Then we have studied about the memory locality. That is, what is the location of the memory with respect to the reference. That is where the data will be stored in the memory. That is known as the memory locality. Then we have studied about how we are exploiting, that is your caching basics, that is your cache memory basics, that how we exploit the temporal locality. This is we have studied about the temporal locality, how we can exploit. Then we also studied about how we exploit the spatial locality. So there are two types of locality. There are two concepts that is used. One is exploitation of the locality of the temporal locality. Another one is exploitation of the spatial locality. Then we also studied how we break the memory into different levels so that memory can be organized in an effective way so that data can be fetched by the CPU very efficiently and effectively. This is the example we have discussed. This is the diagrammatical representation that we have discussed. What is the performance of the two-level memory? This is the hierarchy list. First is registers, L1 cache, L2 cache, main memory, volatile in nature, disk cache that is also volatile, and the last three are the secondary memory and that are of non-volatile in nature. Then we studied about the cache memory, that what is a cache memory. It lies between the main memory and the CPU. Then we have also talked about the cache operations. Then again we talked about the principle of locality, that is your miss and the hit. This is the cache structure, that is your internal structure, how cache looks like. This is the internal structure we have studied. Then how memory will be divided into different blocks. So that's all for yesterday's session. This is the yesterday's session that we have covered in the yesterday's class. Now I'm going to start with a new topic, that is your memory hierarchy, and that is your most important topic because the main name of the topic is also the memory hierarchy, and the topic we have studied or we are going to study is also the memory hierarchy. So this is your memory hierarchy. This says Section 1 and 2 describe some fundamental and enduring properties of the storage technology and computer software. That is, the first topic is your storage technology and another topic is your computer software. We have studied about these two topics. So storage technology means different technologies are used for storing the data. Faster technology costs more per byte than slower ones and have less capacity. The gap between the CPU and the main memory speed is widening. Next, we have studied about the computer software, that is well-defined programs that gives the good locality. So we have studied about these two topics in the section 1 and the section 2. Now, this says in order to, in one of the happiest or happier coincidence of computing, these fundamental properties of hardware and software complement with each other beautifully. Their complementary nature suggests an approach for organizing the memory system. That is, arranging the memory system as a memory hierarchy that is used in all the computer system. That is, we have designed or we are using the memory hierarchy for organizing the memories. Figure 23 shows a typical memory hierarchy. I will show you. In general, the storage devices get slower, cheaper and larger as we move from the high to the lower level. As I told you just right now, that when we come from the top to the bottom, that is from higher level to the lower level, the devices become slower, the devices become cheaper and the devices become larger. At the highest level, that is L0, are a small number of fast CPU registers that the CPU can access in a single clock cycle. Next, there is a SRAM. This is the diagram, figure 23. This is the diagram of the memory hierarchy. One is at the L0. This says smaller, faster and the costlier per byte. That if we go from the low to the high, they are smaller, faster and the costlier. And if we go from the high to the end, that is larger, slower and the cheaper. That is your storage devices. One is your L0, that is registers. So at first location there is a registers. CPU register hold words retrieved from the cache memory. Then at next place there is a L1 cache. Then at next place there is a L2 cache. So look over, this makes a pyramid, that is your hierarchy, that is one after the another level. Then next one is your L2 cache, then L3 cache, then is your main memory. So if I say there are only 4 concepts. Which 4 concepts? One is registers, one is cache memory, one is main memory and one is your secondary memory. How now look like? This is your registers and these 3 types are of cache memory. That is L1 cache, L2 cache and the L3 cache. Then next is your main memory, that is your primary memory. Then local secondary storage, that is your local disk, that is a part of the secondary memory. And then remote secondary storage, that is also a part of the secondary memory. So there are 3 types of memory that is used. Primary, that is your first of all registers, then main memory, that is primary memory, and then secondary memory. And yeah, there is one more memory, that is your cache memory. So registers, cache, main memory, secondary memory. 4 types of memories are used, and these 4 types are divided into 6 lines, that is from 0 to the 6, that is from L0 to L6. At L0 there is a registers, at L1 there is a L1 cache, L2 there is a L2 cache, L3 there is a L3 cache, L4 there is a main memory, L5 there is a secondary storage, and L6 there is a remote secondary storage. So secondary storage is also divided into 2 parts, that is local secondary storage and your remote secondary storage. Local secondary storage means a local disk that is internal to the computer internal to the CPU, and the remote secondary storage is the that is used remotely. For example, distributed system and the web servers. This says CPU holds registers holds words retrieved from the cache memory. L1 cache holds cache line retrieved from the L2 cache. That is, register gets the data from the L1. L1 gets the data from the L2. L2 holds the cache line retrieved from the L3 cache. L3 cache holds cache line retrieved from the memory. That is, the lower version or the below version will be going or give the data to the next version or your higher level authority, that is your L3 cache. In the same way, secondary memory gives the data to the main memory. This says main memory holds the data from the local disk, and the local disk holds the data from the remote network servers, that is your distributed system or web servers. So this forms a pyramid, that is from up to the down or down to the up, and there are different concepts, and this memory hierarchy is divided into 6 levels or 7 levels, starting from L0 and ending with L7. That is, at L0 registers L1 L1 cache, L2 L2 cache, L3 L3 cache, L4 main memory, L5 local secondary storage, and L6 remote secondary storage. So this is your main memory hierarchy. Now, next concept is your caching in the main memory. That is, what is the cache memory, or what is the role of cache memory in the memory hierarchy? This says, in general, a cache, pronounced at the cache or cache, is a small fast storage device. That is, it is a small memory fast storage device that acts as a staging area, or that acts as a mediator between the main memory and the CPU. That is, if CPU wants to fetch the data, then CPU fetches the data from the cache memory and performs the operation, so that operation can be performed in an effective way. So this says this acts as a staging area for the data object stored in the larger, slower device. The process of using a cache is known as the caching. That is, if we use the process, or if we use a cache memory, or if we use the storage device that is your cache memory, that is known as the caching. The general idea of a memory hierarchy is that for each k, the faster and the slower storage device at level k serves as a cache for the larger and slower storage device at level k plus 1. That is, if I am storing the data at k, then it will fetch the data from the k plus 1 location, that is next to the location where the data will be stored. That is, if I'm using the data, or I'm using the location at k, then it will fetch the data for the k plus 1. For example, the local disk serves as a cache for the file. As I told you, if it is k, it will get the data from the k plus 1, that is at the next level. This is the same example. The local disk serves as a cache for files retrieved from the remote disk, like this one. Local disk fetches the data from the remote disk. Over the network, the main memory serves as a cache for the data on the local disk, and so on until we'll get to the smallest cache of all set of CPU registers. That is, first of all, remote transfer the data to the local transfer the data to the main transfer data to the L3 cache, L3 cache transfer the data to the L2 cache, L2 cache transfer the data to the L1 cache, and then go to the registers, and then CPU fetches the instructions from the registers and performs the operation. This is the level by level hierarchy. That is, at first level there is a registers, second level there is a cache memory. So if a cache memory is used, then it can hold the data, or it can fetch the data from the next location, that is your k plus 1 location. This shows a diagram that is a level K and level K plus 1. Smaller, faster, more expensive device at level K caches a subset of the blocks from level K plus 1. That is, it gets the data from the K plus 1. This is also a larger, slower, cheaper device at level K1 plus is partitioned into the blocks. This says data is copied between the level in block size transfer rate. The data is copied from this one, that is first of all 4, then 9, then 14, then 3, that is required of the cache. This shows how data will be fetched from the lowest part, that is the next level. Now let's see with the help of PPTs what is cache memory and what is memory hierarchy. The chapter number 6, the memory hierarchy, continued. This is the memory hierarchy topic. This says what is the introduction, that is why we are using the memory hierarchy. The first point says programmers wants unlimited amount of memory with low latency. That is, programmer needs the unlimited amount of memory, that is there is no limit of the memory with the low latency. Latency means there is no disturbance in the access time. Second point says fast memory technology is more expensive per bit than the slower technology. If I am using the registers, they are more expensive as comparison to the main memory. So this says fast memory is more expensive than the slowest memory. Now what is the solution? How we can achieve n number of memories so that we can target or we can get the benefits from all the memories. The solution is that organize the main memory system or organize the memory into the hierarchy. That is, dividing the main memory or dividing the memory into different concepts into different level, that is organizing into the hierarchy. How we can organize into the hierarchy? First of all, entire addressable memory space available in the largest or the smallest memory. That is, first of all, arrange the memory into different levels. That is, at first level there is registers, then there is a cache memory that is divided into 3 parts, that is L1 cache, L2 cache, L3 cache, then main memory, and then the secondary memory. This is incrementally smallest and the smaller and the faster memories, each containing a subset of the memory below it, proceeds in step up towards the processor. That is your solution to this problem. That is, we are arranging the memory into the hierarchy into the different levels. Next is temporal and spatial locality ensures that nearby all references can be found in the smaller memory. That is, we use the concept of the locality of reference so that we can find that every memory can be found in the nearby location. Now this is a memory hierarchy, a small diagram for the memory hierarchy. First of all, there is a registers, then L1 cache, L2 cache, L3 cache, memory, disk storage. So this is a data bus or the memory bus. As I told you with the help of book, this is the hierarchy, or this is the diagrammatical representation of the hierarchy. So first of all, there is a registers, then 3 types of cache memory, that is L1 cache, L2 cache, L3 cache, main memory, and then at last disk memory reference, that is your secondary memory. This is the memory hierarchy for a server, and this is memory hierarchy for a personal device, that is your computer. Same concept. First of all, there is a CPU registers, but in this there are only 2 types of memory. Why? The capacity is not too high, that is equivalent to the server, but this is the capacity that is middle or at the middle level. There are 2 types of cache memory, that is L1 cache and the L2 cache, and then there is a memory that is your main memory, and then it is attached to the storage, that is your flash memory. This is the memory hierarchy, how we can divide the memories into the different chunks into different levels. This is the memory performance gap, that is the processor and the memory. There is a huge gap between the processor and the memory in the coming days, in the coming years. In 1985 there is a less gap, 1990 there is a more gap than the 85, and now in 2010 there is a huge gap between the memory and the processor. So we use the concept of memory hierarchy so that processor can get the data from different memories, and different memories communicate with each other so that they get the data and pass the data to the processor. Memory hierarchy design, that is how memory hierarchy designs. This says memory hierarchy designs become more crucial with recent multi-core processor. That is, if we are using the multi-core processors or multiple processor, that then memory hierarchy design is more crucial, because I'm using more than one processor. That is your multi-processing or the multiple processor or multi-core processor. Then memory will be designed or memory will be arranged as per the requirement of the processor. So that is very crucial part with respect to the multiple processor. Suppose I'm using only one processor, then it's okay. There is no hard and fast rule, or there is no cruciality for designing the computer. But if I'm using the multiple processor, then it is very crucial to arrange the or design the memory. Now, why it is so crucial? Because the aggregate peak bandwidth grows with the number of cores. That is, if there are number of cores or there are number of processors, then the peak bandwidth or the bandwidth of the computers increases or the grows. Suppose, for example, Intel Core i7 can generate 2 references per core per clock. That is, the i7 is a new technology, new Intel Core that is used, that uses the 2 reference for the memory for per clock. Then next says 4 cores and 3.2 gigahertz cores. That is the capacity of this one. Dynamic RAM bandwidth is only 6% of this, that is 25 GB. Then it also requires, that is when we design the memory hierarchy, it also requires multiport pipeline cache. That is a multiport systems, and the pipeline cache, 2 levels of cache per core. That is, if there are 4 cores, that is there are 4 processor, then we need the 8 level of cache, that is L1, L2, L3, L4, L5, L6, L7, L8. So each core requires 2 level of cache or 2 levels of cache. Then next point says shared 3 level cache on the chip. That is, on the server it requires 3 level of cache. That is, if there is only one processor, then it requires L1, L2, L3, and if there are large number of processor, then it requires another number of caches, that is multiplied by the 3. Then what is the performance and the power? That is how much power it will take, and what is the performance that it gives by when we are using the memory hierarchy. This point says high-end microprocessor have more than 10 MB on the chip cache. It consumes large amount of area and the power budget. Next, what is the terminology that is used in the memory hierarchy? One is your hit, as I told you, when the data is available or when the data is fetched by the processor from the cache memory, or if data is available in the cache memory, then it is known as the hit. That is, data appears in some block in the upper level. Upper level means from the cache memory itself, example block X. Hit rate. Now, what is the hit rate and what is the hit time? The rate or the hit rate, the fraction of memory access found in the upper level. That is the rate by which the memory is fetched or the data is fetched from the upper level, that is known as the hit rate. Next is your hit time. That is the time taken to access the upper level, which consists of that is the time that takes, which consists of the RAM access time plus the time to determine hit or the miss. Miss is the concept when the data is not available in the cache memory, then the CPU fetches the data from the main memory. That is, data is not available or data is not get from the cache memory, so there is a miss. That is, data is not available in the cache memory and the CPU approaches to the next memory, that is your main memory. So that is your miss. So there are two concepts, one is hit and one is miss. The data need to be retrieved from a block in the lower level. Lower level means your main memory, that is your miss. This is your miss rate, that is 1 minus hit rate. The hit rate is the fraction of memory access found in the upper level, and the miss rate is the 1 minus the hit rate. Then what is a miss penalty, or what is a miss penalty? That is the time to replace a block in the upper level plus the time to deliver the block the processor. Now next point says hit time is less than the miss penalty, that is 500 instructions on 21264. This is the upper level memory, that is your block X. This is the low level memory, that is the block Y. This is the processor. It is going to the processor. It is coming from the processor. This slide says there are two concepts. There is a hit and there is a miss. When the data is available at the upper level, that is in the cache memory, that is the hit. If data is not available from the upper level and goes to the down level, that is the main memory, that is your miss. Now, how we measure the caches? That is our cache measures. Same concept, hit ratio or hit rate, that is the fraction found in that level. So high that usually talk about the miss rate, that is your miss rate fallacy, that is SMIPS to CPU performance. This is the same concept. Now, average memory minus access time equals to hit time in plus the miss rate into the miss penalty. Then what is a miss penalty? That is the time to replace a block from the lower level, including the time to replace in the CPU. That is a miss penalty, as I discussed in the last slide also. Now, there are 4 questions that arises for the memory hierarchy. Where can a block be placed in the upper level? That is your block placement. Then how is a block found if it is in the upper level? That how we can find the block? First of all, where? What is the location of the block? Then how is a block found if it is in the upper level? That is identification of the block. Then which block should be replaced on a miss? That is next question arises, which block we used or which block should be replaced on a miss? That is your block replacement. Then what happens on a write? That is when we write something on the memory, that's what happens on the write, that is your write strategy. The first question, where can be a block is placed? The answer of the first question is block 12 placed in the 8 block cache. That is fully associative, direct mapping, two-way set associative. This is where the data or where the block can be placed in the upper level. That is set associative mapping equals to block number modulo number sets. That is using the modulus operation with the block number and the number set. This is your cache, this is your main memory, this is your fully mapped, this is your direct map, and this is your two-way associative. That is done by using the block number, that is 12 mode. There are number of sets are 4, that is 12 mode 4. In the same way, direct mapping, there is a 12 mode 8. There are 8 number of sets that is available. In this there are 4 number of sets available. Why 4 number? There are total 8 number of bits available, and this is a two-way associative. So half of the 8, that is 4, that is 12 mode 4. This is a direct map, that is 8 bits used, that is 12 mode 8. And 12 is the number of block that is placed in the 8 block cache. Now next is your how is a block found if it is in the upper level? How we can find the block that is available in the upper level? So the output or the how we can achieve the target or how we can find the block by tagging on the each block. We can tag on the block, we can put the tag that is of 4 bits. So we can tag on the each block. No need to check index or the block offset. That increases the associativity, shrinks the index, expand the tag. Then which block should be replaced on a miss? That is which block should be replaced when there is a miss? Easy for the direct map, that is it is easy to replace for the direct map, that is your direct mapping access, set associative or fully associative. Then next question is after a cache reads a miss, if there is no empty cache block, which block should be removed from the cache. The least recent used block, that is not used on a regular basis, that is when least recent used can be empty or can be removed from the cache memory. What happens on a write? This is a write through and write back. This is the policy. That is data written to the cache block also written to the low level memory. That is a write through. That is, if the data is written on the cache memory or written to the cache block, is also written to the low level memory or the low level memory concept. That is your main memory, secondary memory. Then next is your write back. This is your write through. Next is your write back. This writes the data only to the cache. That is writing the data only to the cache memory. Update levels, lower level when a block falls out of the cache. In this, data is written to the lower level as well as the cache block. But in write back, data is only written to the cache memory. Update the lowest level at the end of the place or at the end of the period. Next, debug. That is, it is easy to be debug in the write through and it is hard to debug for the write back method. Next point, do read misses produces write? If there is a write back, yes, it is the read misses that produces the writes and there is no in the write through. In the same way, repeated writes makes it to the low level, yes in the write through and no in the write back. Next, write buffers for the write through caches. This is the write buffer for the write through cache. That is, data is written in the lower level memory as well as in the high level memory. That is a cache. Holds data awaiting write through to the low level memory. Why a write buffer? So CPU does not store. Why a buffer? Why not just one register? Burst of writes are common. So this is the example of some common technologies. Are read after write, that is RAW hazards an issue for write buffer? Yes. Next is your memory hierarchy basics. That is, if a word is or when a word is not found in the cache, a miss occurs. As I told you, fetch words from the lower level, that is your main memory in the hierarchy, require a high latency reference. Then lower level may be another cache or the main memory that I told you. It may be another cache, that is L2 cache, L3 cache, or maybe in the main memory. Then next point is also fetches the other words contained within the block. Then places the block into the cache in any location within the set determined by the header. That is, if a word is not available in the cache, a miss occurs and the following operations will be performed if the word is not available in the cache memory. This is where n sets equals to n way set associative. There are two types of mapping technique in this, that is direct and that is fully associative. Then how to write to the cache, means what are the technologies that is used, how we can write in the cache. As I told you, there are two technologies, that is write through cache and the write back cache. In write through, low level as well as the high level will be written at the same time, but in write back only the lower level will be updated when the upper level is replaced. Then miss rate we have discussed, the fraction of cache access that results in the miss. Then what are the causes or what are the consequences of the misses? That is compulsory, capacity, conflict. This is your formula for the miss, that is misses upon my instruction equals to miss rate into memory access divided by instruction count, that is miss rate into memory access divided by instruction. That is the same concept. This is multiplied by this one, this is the different one by this one. This is the misses of the instruction, that is average memory access time equals to hit time plus miss rate into the miss penalty. This is the formula that is used. Note that speculative and multi-threaded processors may execute other instructions during a miss. This is the memory hierarchy basics, that is 6 basic cache optimization. First one is your larger block size. First one is your larger block size. This is how we can optimize the cache or optimization of the cache memory. That is reduces the compulsory misses, then increase the capacity and conflict the misses, increase the miss penalty, then larger the total cache capacity to reduce the miss rate. That how we can optimize the cache memory so that data will be fetched by the CPU efficiently and effectively. So these are the cache optimization. The first is your larger block size. That is the larger we can maintain the large or the large size of the cache. That is a larger block size. Then larger total cache capacity to reduce the miss rate. That is the capacity of the cache memory is too high so that it will contain all the data and there is no miss rate of the cache memory or of the data. Then higher associativity, that is reduces the conflict misses, increases the hit time. These are the basics, that is how we can optimize the cache memory. Then giving the priority to the read misses over the write. Then next one is your high number of cache levels, then avoiding the address translation in the cache memory. So these are the 6 methods how we can optimize the cache memory. These are the 10 advanced of the optimizations. Small and fast first level caches, that is critical timing path, addressing the tag memory, then comparing the tags and then selecting the correct tag. That is how we can optimize the advanced optimization techniques. So small and the simple first level caches, that is uses the critical timing path, that is first of all addressing the tag memory, then compare the tag and then select the correct tag. This says direct map cache can overlap the tag, compare and transmission of the data. Low level associativity reduces the power and because fewer lines are addressed. This is the diagram that is shown. This is the L1 size and associativity. This is one way, this is 2 way and 4 way, 8 way. So black is represented by only 1 way. Or then gray is represented by 2 way, then 4 way and then 8 way. So these are represented in a different kilobit. This is a cache size. Then 16 bit, 32 bit, 64, 128, 256. This is the access time. This is again the access time. This is the access time in hundreds multiple, that is in discrete value. This is in decimal form. Then next is your way prediction. That is how we can predict, that is your way prediction. So this is the next topic that is started. First of all, let's see with the help of book that what we have covered in the book. This is your cache 8. As I told you, when a program needs a data object D from the level k plus 1, it first looks for the D. As I told you, it first looks for the cache memory. If the data is available, this is if D happens to be caches at level k, then what we called at the cache hit. That is, if data is available at the k location, that is in the cache location, that is known as the hit. And if the data is not available in the k location, that is available from the lower level location, that is k plus 1, that is known as the miss. This is the cache miss. If on the other hand the data D is not caches at the level k, and then we have what is known as the cache miss. Now let's take 5 to 10 minutes break and then come back starting with the kinds of cache misses. So let's take 5 to 10 minutes break. That is, what are the kinds of caches misses? That is, if a cache or the data or instructions is not available in the cache memory, then the CPU must go to the next level, that is the lowest level or the main memory. Then what are the types of misses available? That is the kinds of cache misses. This says if the cache is level k is empty, then any access of any data object will miss. That is, object will miss. An empty cache is sometimes refers to an cold cache. That is, if the cache of the data is not available in the cache memory, that is an empty cache, that is known as the cold cache. And the misses of these kinds are known as the compulsory misses or the cold misses. Then cold misses are very important because they are often transient or even that might not occur in a steady way or steady state after the cache has been warped up for the repeated task. This says that kind of cache is a cold cache. That is, if the cache is empty and data is not available in the cache memory, that is known as the cold cache or the cold misses. Restrictive placement policies of this kind led to a type of the miss known as the conflict miss. That is your next miss. One is your cold miss, then is your conflict miss, in which the cache is large enough to hold the reference data object, but because they map to the same cache block, the cache keeps missing. That is, the cache is large enough to hold the data. That is, cache is not less, but is it large enough, but because they map to the same cache block, the cache keeps missing. Because they reference to the same cache block, so the cache becomes missing and we cannot fetch the data, or the CPU cannot fetch the data from the cache memory. That miss is known as the conflict miss. Next is your cache management. But before this, let's take in the slides. Then next slide, that is your wave prediction. That is how we can predict. That is your wave prediction. This says to improve the hit time, predict the way to preset multiplexer. That is your MUX. This says misprediction gives longer hit time. That is, misprediction or the misprediction gives the longer hit time for the improvement. That is your prediction accuracy 95 or the 90% for the two-way, or the 80% for the one-way or the four-way. I caches have better accuracy than the D cache. This says first used on the MIPS, used on the ARM. This is the extent to predict the block as well. This is your pipelining cache. That is, what is the pipelining cache? That is, pipeline cache access to improve the bandwidth. As I told you, pipelining means more than one task at the same time. So pipelining cache means using the two caches at the same time to improve the bandwidth. That is, two cache memories are used by the CPU to fetch the data, so that bandwidth, so that speed will be increased, and we can, or the CPU can fetch the data and performs the operations efficiently and effectively. Example, Pentium 1 cycle, Pentium Pro, Pentium 3 2 cycles, Pentium 4 2 Core i7. That is, this is the processor. These are the processor. That is, if I'm using Pentium 4, Core Dual 2, i7, i5, i3, that requires or that uses 4 cycle. That is 4 caches, or the 4 blocks can be used at the same time. That is your 4 cycles. Then what is the advantage of pipelining? It increases the branch miss prediction penalty, then makes it easier to increase the associativity. Then non-blocking caches, that is non-block cache. What is the use? It allows the hits before previous miss complete. That is your non-block cache. Hit under the miss. Next is your hit under the multiple misses. Then L2 must support this. In general, processor can hide L1 miss penalty, but not L2 miss penalty. So this is the non-blocking cache, that why the cache is not blocked. Then multi-banked cache, that is how we can organize, or how we can arrange the cache in a multiple way or in a multiple links. That is, organize the cache as an independent banks to support the simultaneous access. That is, we are using the pipeline cache so that independent banks supports the simultaneous access. ARM Cortex A8 supports 1 to 4 bank for L2 cache. Intel i7 supports 4 banks for L1 and 8 banks for L2 cache. So these are the categories, how different caches memories are divided into the simultaneous access into the independent banks. Then next point says interleaved banks according to the block access. This is your bank 0, the bank 1, bank 2, bank 3. These are the block addresses, that is at 0 location, 4th location, 8th location, 12th location, and this is your bank 1, that is at the 1st, 5th, 9th, 13th, bank 2, 2, 16, 10th, 14, that is a block address. So at bank 0, 0 address, bank 1, 1, bank 2, 2, bank 3, 3. Then bank 0, 4th address, bank 1, 5th address, bank 2, 6th address, bank 3, 7th address. So it starts from the 0 and go to the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So these are the different banks that divide the cache memory into different banks. This is 4-way interleaved cache banks using the block addressing. Then critical word first early restart. That is how critical words firstly fetch from the cache and then early restart. This is a critical word first. Request missed word from the memory first. That is, if the CPU or the cache memory does not contain the data that is required by the processor, then first of all cache memory request for the another memory, that is the lowest memory for the missed word. Even though it has a word, but if it has a missed word, that is the word that is required by the CPU is not available in the cache memory. So first of all cache memory request for the missed word from the memory first, then is sent to the processor as soon as it arrives. That is, first of all it requests for the lowest level memory, that is the main memory for the word, and then it passes to the processor as soon as it arrives. It means the cache memory passes the data to the processor. Then early restart, that is request for the words in normal order, then send the missed word to the processor as soon as it arrives. That is an early restart, request the words in a normal order, send the missed word to the missed word as soon as it arrives. Effectiveness of these strategies depends on the block size and the likelihood of another access. That is, it depends on the scenarios. What is the scenario, what is the block size, and what is the likelihood of another access. Then next is your merging the write buffer. Then when storing to a block that is already pending in the write buffer, suppose I'm storing the data in the block that is already pending in the write buffer, that is if there is any buffering, that is some data will be buffer. Update the write buffer. Reduces the stores due to full write buffer, do not apply to the input output address. This is no write buffering, there is no write buffering, there is a buffering, that is where this is the vacant place, this is the vacant place, and this is the vacant place. So this is the write buffering and this is no write buffering. Then compiler optimization. How we can compile the optimization technique. So these are the multiple restrictions. These are the multiple data that is available for the compilation for the optimizing the compilers. First is your merging arrays, then loop interchange, then loop fusion, then blocking. These are the 4 types of data on which we can compile the data for the cache memory. This is your merging array example. This is the example that is used for merging the data. This is before 2 sequential array that is using the val size. This is a fixed size. This is the key, that is a variable name. There is a size. That is after 1 array of structure that is using the structure, that is merge, taking the 2 variable, that is val and the key, then using the variable name, that is merged array size. This is your loop interchange, this is your merging array, this is a loop interchange example, this is loop fusion example, this is a blocking example. So these are the 4 concepts for data that is used in the compiler optimization, that is merging arrays, loop interchange, loop fusion, and the blocking. This is the loop interchange. This is the interchange of the loop, that is I equals to 0, I is less than 5000. Here it is in the inner loop, here it is in the upper loop. Here it is going to the outer loop and going to the inner loop. That is, the outer loop is converted into the inner loop and the inner loop is converted into the outer loop. That is a loop interchange. Then loop fusion, that is, the operation will be altered. That is, the multiply is converted into the plus. This is your multiplication, that is converted into the plus operation. Then this is the blocking example. This is the block that we have used. Two inner loops, that is the example. This is the capacity. This is the main idea. Then this is the example of the blocking. Then hardware prefetching, that is how we can prefetch from the hardware part. This is first of all how we can achieve the prefetching or the fetching from the hardware. First of all, fetch the two blocks on the miss, include next sequential block. So fetches the two blocks on the miss. Then next is your compiler prefetching. This is your hardware, this is your compiler. How we can prefetch or prefetch. First of all, insert the prefetch instruction before the data is needed. That is, first of all, insert the instructions before the data is needed by the compiler. Then non-faulting, that is, prefetch does not cause the exceptions. Then register prefetch, that is, loads the data into the register. Then cache prefetch, that is, loads the data into the cache. These are the two kinds of prefetch, that is, register prefetch and the cache prefetch. In register prefetch, loads the data into the register, and in cache prefetch, loads the data into the cache memory. This is a compiler prefetching. Then next one says combined with the loop unrolling and the software pipelining. So this is combined with the loop unrolling concept and the software pipelining. This is the summary what we have covered in the last slides. This is the technique that is used, small and simple caches. There is a hit, there is a power consumption, that is plus. There is a way predicting caches, there is a hit time and the power consumption, hardware complexity, yes, used in the Pentium 4. This is the pipeline cache access, bandwidth is high, hardware complexity is there, that is cost is high, most widely used. In the same way, these are the different techniques and these are the different comments that is available on the cache memory. Then memory technology. Then memory technology means what are the techniques or what are the technology that is available or that can be performed on the memory. First is your performance metrics. That is how we can achieve or how we can measure the performance of the memory. That is a performance metric. Metric means measurement. First of all, the first point is latency is concern of cache. That is, latency is mostly available in the cache memory. Bandwidth is concern of the multiprocessor and input output. That is, bandwidth it reduced or is a major concern in terms of the multiprocessor. That is, when we are using more than one processor, then bandwidth is mostly affected. Then access time, that is your time between the acknowledgement or between the request and the getting word. That is the time between the read request and when desired word arrives. Then cycle time, that is the minimum time between the unrelating caches to the memory. That is a cycle time. Next point says dynamic RAM used for the main memory, static RAM used for the cache. That is, when we are using the dynamic RAM, that is used for the main memory, and when we are using the static RAM, that is used for the cache memory. These are the memory technology that is used. One is static RAM, one is dynamic RAM. Static RAM requires low power and the dynamic RAM requires more power. Static RAM requires 6 transistors. Dynamic RAM, it must be rewritten after being read, must be periodically refreshed. So this is the difference between the static RAM and the dynamic RAM. That is a part of the RAM that is divided into two parts, RAM, that is static RAM, and the dynamic RAM. So static RAM requires low power and requires 6 transistors, Dynamic RAM must be refreshed within a periodic basis, that is within 8 microseconds, must be rewritten after being read. 1 transistor per bit, that is static RAM requires 6 transistors, but dynamic RAM requires only 1 transistor. Then address lines are multiplexed. Then this is the Amdahl's law that we have discussed in the last two classes. Amdahl's law, that is memory capacity should grow linearly with the processor speed. Unfortunately, memory capacity and speed has not kept pace with the processor. Then some optimization techniques, that is your synchronous RAM, dynamic RAM, double data rate, that is DDR, multiple banks on each dynamic RAM device. This is a memory optimization table that is in production year 1980. Chip size is of 64K bit. Dynamic RAM is used. 180 nanosecond is used. Fastest is 150, and the column bit rate or the transfer rate is 75 nanosecond, and the cycle time is 250 nanoseconds. So these are the multiple configuration that is used for the memory optimization. One is starting from year 1980. This is for the year 2012. This requires, or the chip size is of 8 GB or the 8G bit. This is the dynamic RAM 3. Then slowest dynamic RAM, that is 30. Fastest, that is 24. Then column access drop, that is the data transfer rate, that is 0.5, and the cycle time is 31. This is the table that is used for showing the memory optimization techniques. This is again the next diagram. This is your standard. This is the dynamic RAM used. This is your DDR that is required, or that contains 3 parts: DDR2, DDR3 and DDR4. And DDR is a dynamic data rate. This is a double data rate, not dynamic. This is double data rate. There are 3 parts: dynamic data rate 2, DDR3, DDR4. This requires low power, higher clock rates. This requires 1.5 volts, 800 megahertz, 1 to 1.2 volts, 1600 megahertz. So this contains 3 parts, that is DDR2, DDR3 and DDR4. Then GDDR5 is a graphic memory based on the DDR3. What is a graphic memory? That achieves 2.5 into bandwidth per dynamic RAM, that has a higher bandwidth, wider interfaces, higher clock rate, reducing power in static dynamic RAM. So this is the old concept that is used in the memory optimization. Then memory power consumption, that is what is the power that is required. This is your low power mode, this is your typical usage, and this is your fully active mode. This is our power consumption that is taken in the terms of watts, that is in megawatts, that is power in terms of megawatts. So the dark line or the dark shade is used for the read, write, terminate power, and the light is used for the activate power, and this is used for the background power. So this is your low level, that is your only this part, that is background color, that is typical storage. This contains 3 parts, and this is fully active, that contains 3 parts. Next, what is a flash memory? That is a type of the EEPROM, that is your erasable programmable read-only memory, that is your flash memory. Then flash memory must be erased before being overwritten, that is it must be erased before using the next part or before being overwritten, and flash memory is non-volatile in nature. Then limited number of write cycles, that is it contains limited number, that is predefined number of write cycles. Then it is cheaper than the static RAM. Why it is cheaper? Because it takes less power. It is cheaper than the static dynamic RAM, but more expensive than the secondary storage device, that is your disk or tape. Then it is slower, that is flash memory is slower than the static RAM and faster than the disk. Then memory dependentability, that is how what memory is dependent on which memory. That is, memory is susceptible to the cosmic rays. Then there are two types of error that is used. One is soft error and one is hard errors. Soft errors are generally dynamic error, that is dynamically it is used, that is detected and fixed by the error correcting codes. That is your soft errors, that is detected by the detected and fixed by the error detecting code or the ECC, error correcting code. Then there is a next concept, that is your hard error, that is a permanent error. This is a dynamic error that can be rearranged, that is a soft error. And then there is a hard error, that is a permanent error, that is not restored or that is not dynamic in nature, that uses the sparse rows to replace the defective rows. Next is your virtual memory, that is protection via virtual memory. Keeps processor in their own memory space. What is the role of virtual memory? It provides the user mode and the supervisor mode. It protects the certain aspect of CPU state. That is, virtual memory is used as an enhanced memory or is used as an add-on memory when data is not efficient or is it not available or it is not stored in the main memory. Then uses the next concept, that is your virtual memory. So it provides a mechanism for switching between the user mode and the supervisory mode. Then provides a mechanism to limit the memory access. Then provides a TLB, that is transition link table or translate look table to translate the addresses. So these are the concepts that is used, that is virtual memory, that is used in the protection. Then what is the virtual machines? It supports the isolation and the security. That is, virtual machine provides the isolation, that it works in the isolation and provides a sense of security, that is CIA, confidentiality, integrity and availability. It shares a computer among many unrelated users, enables by row speed of processes, blah blah blah. So there are so many features available for the virtual machines. Then impact of VMCs, that is virtual machine on the virtual memory. That is, what is the impact of the virtual machine on the virtual memory, or what is the impact of virtual machines on the virtual memory. That is, each guest OS maintain its own set of page tables. That is the main concept. It requires VMM, that is virtual machine, to detect guest changes to its own page tables. Then occurs naturally if accessing the page table pointer is a privileged operation. So these are the impacts on the virtual memory. Now let's see with the help of book. Then it's your cache management. That is, this says, as we have noted, the essence of the memory hierarchy is that the secondary storage at each level is a cache for the next low level. That is, at each level there is a concept of the next level, that is, if data is not available in the same level, that is going to the next lower level. That is, at each level some form of logic must manage the cache. By this we mean that something has to partition the cache storage into blocks, transfer rates, transfer block between the different levels. For example, the compiler manages the register files, the high level of the cache directory. It decides when to issue loads, when there are misses, and determine which register to store the data in. The caches at level L1, L2, L3 are managed entirely by the hardware logic builds. Then summary of the memory hierarchy concepts, that is the what we have covered in the memory hierarchy. To summarize, memory hierarchy based on the caching work because slower storage is cheaper than the faster storage and because program tend to exhibit locality. So these are the summary, that is why we are using the memory hierarchy or cache memory. First of all, there is exploiting the temporal locality and exploiting the spatial locality. That is the main advantage why we are using the memory hierarchy. Caches are used everywhere in the modern systems. As you can see, caches are used in the CPU chip, operating system, distributed file system. This is the diagram, that is cache is used everywhere. This is the type, this is what cached, this is where cached, and this is latency, and this is managed by. So this is a CPU register is the type, then what cache, that is what type of it is cached, that is 4-bit or 4-byte or the 8-byte words, and where it is cached, either on the CPU register, on the chip of the CPU registers. There is no latency, and this is managed by the compiler. So this is the what we have covered in the memory hierarchy. Next topic is your cache memory, that I will start tomorrow in tomorrow's class. So that's all for today's session. Now, if you have any questions, please text the questions and I will answer you. But before that, let's take a quick review what we have covered in the today's class. In today's class, we have started with the memory hierarchy. We have introduced what is memory hierarchy, why we are using the memory hierarchy, what is the main motto of using the memory hierarchy, that is why we are arranging the or organize the memory system into the hierarchy. This is the diagram we have covered in the memory hierarchy, that is CPU registers, L1 cache, L2 cache, L3 cache, and the main memory. Then there is we have shown the gap, performance gap between the memory performance gap. Then memory hierarchy design, or what is the designing that is available for the memory hierarchy. Then what is the performance, we have discussed what is the performance and what is the power consumption. Next is your memory hierarchy terminologies, that is what is the memory hierarchy terminologies, what is the terminologies that is used in the memory hierarchy, that is your hit and the miss. Hit means if the data is available in the upper block, that is in the cache memory, that is your miss. That is your hit. And if data is not available in the cache memory and going to the low level memory, that is your main memory, that is your miss. So there are two concept technology that we have studied, that is your hit and the miss. This is our cache measures, that is how we can measure the hit ratio and how we can measure the miss ratio. These are the questions we have studied, 4 types of questions. Then what is the difference between write through and the write back? Then we have studied about the basics, that if data is not available or the word is not available in the cache, then miss occurs. This is the N sets, writing to the cache. There is a miss rate, causes of the miss rate, formula for the miss rate, or formula for calculating the miss ratio. These are the some basics, that is memory hierarchy basics that is used. There are 6 basic cache optimization technology that is used. These are the tips for the simple first level caches. Then L1 size and associativity we have discussed with the help of diagram. Then way prediction, that is how we can predict. Then we have also studied about the pipeline cache, that is how different cache memories are used in parallel, that is pipeline cache. Then non-blocking caches. Then we have studied about how we can achieve, or how computer will achieve, by first of all critically word first and then early restart. Then how to merge the write buffer. Then how to optimize with the help of compiler, that is compiler optimization. There are 4 parts, there are 4 categories. One is merging the arrays, then loop interchange, then loop fusion, and then blocking. These are the examples of 4 concepts. Then we have studied about the hardware prefetching, that is how we can how we can fetch the hardware components by using the prefetch. Then compiler prefetching. Then what is a summary that is used, or that is the technique that is used and the comment they have arrived. Then memory technology. Then how we can measure the different memories, that is the performance metrics. Then memory technology, that is divided into 2 parts, that is static RAM and the dynamic RAM. Then MDEL's law. This is a DDR. Then graphics memory, flash memory. We have studied memory, how memory will dependent on the other memory. Then what is a virtual memory, what is the role of the virtual memory. Then what is a virtual machine, that is VM, and what is the impact of virtual memory on the, or virtual machine on the virtual memory. So that's all for today's session. Now if you have any doubts, then please text the doubt and I will answer you. In tomorrow's class, I will start with the new concept, that is your cache memory. So this is your next topic, cache memory in detail. Today I've discussed some topics like cache, hit, miss, but in tomorrow's class I will discuss the details version of the cache memory, that is what is L1 cache, what is L2 cache, what is L3 cache. So this is your next topic, that is your tomorrow's topic. So now if you have any doubt, then please text that out. Thank you so much everyone. Bye bye.